What's up, guys? Welcome back to the podcast. So we got John Ellis on the show. He is enthusiastic, is the term I would use to describe his passion for indoor air quality. Now, he goes through 6 pillars, his own sort of defined pillars of what indoor air quality should withhold. And we go through that on this particular episode. There will be a part 2 with John as well. So stay tuned for that one. This is the HVAC Know It All podcast, and I'm your host, Gary McCreadie. This podcast is sponsored by Cool Air Products, Master, Cintas, and SupplyHouse.com. Go to the show notes and click on the links to check these guys out. All right, John. So thank you for your time to hop on here. And I know that indoor air quality is something you're passionate about. I've gone the deep dive in indoor air quality multiple times when it comes to filtration, humidification, ventilation. All those types of things are really important. So let's get your take on indoor air quality, just your initial thoughts on it first, and then we'll get going.
Yeah. So again, thank you for having me on the show. I'm 43 years HVAC strong. That's my roots. 20 of those years I've spent in building science as well. And so one of the things I like to say that building science, HVAC, and indoor air quality are inseparable. It's the trifecta of building better environments and how they dovetail together. You mentioned a couple of the things that you look at indoor air quality, and those align with what I have to look at. And so I have 6 key principles. And one would be thermal comfort. I mean, we are in the comfort business. And a lot of times we take thermal comfort for granted, and that means different things to different people. But anybody that is compromised, thermal comfort it is essential because their condition can exacerbate or exaggerate how their body feels when experiencing thermal comfort. And ironically enough, people who are compromised can actually feel pressures in a home, and that can affect them. So we got thermal comfort, and then we have to talk about humidity control, too much of the lack thereof. And that is going to be contingent on what part of the country or what your climate is and what that looks like for different people. You know, up north, Canada, Michigan, Indiana, Minnesota, upstate New York, they have to address it on both sides. So they have dehumidification during the summer, and then they have humidification during the winter. And of course, then bringing in my next topic would be ventilation. So we got to put the V back in HVAC. One thing I teach in my classes is the why never changes, just the how. So how I do ventilation in California, Arizona, Utah, Nevada, even my home state of New Mexico is going to look a lot different on how we do ventilation in Houston, Texas, Louisiana, Georgia, Alabama, Florida, right? So the why never changes, just the how. So we've got thermal comfort, we've got humidity control and ventilation, and then we can't have good indoor air quality without filtration. And so we have a whole host of different filtration methods that are out there. Everything seems to be leaning towards between MERV 8 and MERV 13, which is a good thing. But cause and effect, we can't just throw a filter in a system without it having to have been designed. You know, we hear stories all the time about clients going down to the big box store and they buy the allergy buster and they put it into their system and it's got huge static resistance.
Chokes off the airflow.
Yeah, then we got all kinds of problems and failures that come with that. So cause and effect. So as we move forward, I like to dip my toe into the building science aspect, and we got to look at building pressures. And with building pressures, we have infiltration. And then what are those driving forces of infiltration? You know, we want to keep inside in and we want to keep outside out. By paying close attention to building pressures, we're able to mitigate or at least have some sort of control over that. In the HVAC realm of things, if we're going to do any kind of accurate load calculation, one of the biggest numbers we can plug in would be our infiltration rate. And that really gives us an accurate account of what the house is doing and how the house and infiltration can impact our loads and being able to be accurate with that. And then my sixth one, which is last but not least, would be pollutant identification and then source control. We can't fix what we don't know about. And so if there's certain pollutants in the home and we can identify them, that would give us a good clue or indicator on where they're coming from. Are they outside coming in? Is it products and building materials that we've brought into the space? Do we have a buildup of pollutants because we've got substandard ventilation? And so those are the kind of the 6 key principles that I like to hone in on that should be part of our everyday HVAC businesses already. And then we can go further than that. But those are my foundational 6 principles.
So let's go back to one. When you said thermal comfort, you're just talking about the sensible temperature in the room. Is that basically what you're talking about?
We can't look at thermal comfort without looking at sensible and latent.
Okay. Well, just because thermal comfort and humidity control were 2 different things. So that's why I was asking you, maybe define thermal comfort for us. So that should be the question that I'm asking you.
And sure, so thermal comfort would be the wide range of things, and it means something different to different people. So it would be controlling a temperature in a space. And then we have our sensible, and we have our latent. And of course, the latent side would move into humidity control. We can have a latent capacity in a home without having high humidity, no matter where you're at. And so that is the work, the actual work that an air conditioning system does. It's doing sensible, it's doing latent. How you design that piece of equipment and the ratio is going to look different from one side of the country to the other. And then when we get into humidity control and we're looking at latent, sometimes the HVAC system's not going to be able to keep up. And then so we would have to look for supplemental dehumidification to help us with that latent load or that latent side of the work that the air conditioning system's doing. Does that make sense?
Yes, it does. So if we're adding supplemental latent control, like a dehumidification system, what are your thoughts? Like a standalone system with a drain that just goes down into a drain, or attaching it to the actual HVAC system that's installed in the home? What's your thoughts, preferences there?
Again, the why never changes, just the how. Of course, when we start to look at introducing a dehumidification system into our existing HVAC, I mean, one, is there room? Does it make sense? Is there a budget for it? But, having a portable dehumidifier, let's say in a basement, just to help with that latent coming from infiltration from a basement, could be enough. That's a loaded question. And and I've seen the gamut on how we need to accomplish that. And then when we're looking at ventilation, again, the why never changes. Are we adding to our latent load just by the fact of bringing in outside air on a humid day based on what climate you live in?
Yeah, most definitely are. If we're living in a humid climate or a humid period of that specific area, I mean, we go through humid periods in July and August, sometimes even June, but we need to still bring in fresh air. So how are we going to, let's talk about this for a minute. So we have to bring in fresh air. We want to keep the space, because you talked about building pressure. So if we want to keep the space under a slight positive, and we want to bring in ventilation, but we want to control the humidity at the same time because we're adding extra load now to the building envelope, what are some strategies there that we can use to accomplish this?
There's been a lot to do about ASHRAE 62.2. And that's a minimum standard, and that's based on occupancy, number of bedrooms and square feet. And it's a minimum standard. I've always designed my ventilation to my exhaust from the house. So any kind of appliance that's taking air from the space to atmosphere. So I like to look at that. And then I like to look at my ASHRAE 62.2, and whichever number is greater is going to be my design criteria. So again, we have to understand that standards are minimum. It's a minimum standard. So if I've got a 1,500 square foot home, it's got 3 bedrooms, and I look at the table and it could tell me that, hey, I need 64 CFM of outside air just to be able to accommodate that minimum code. But if I've got a large amount of exhaust coming out, I may want to increase that. Now, yes, I will take a slight energy penalty on that, but it's like what we have to pick our battles. Where do we want to go? And so an ERV and HRV are good as well. An ERV doesn't do a whole lot of dehumidification, so we have to understand, where we're at with our climate. And then, there are some parts like California that stay pretty mild in some of the climates. Now, California's got 16 climate zones just in California. And so just having a simple strategy of bringing in a duct and bringing it right into the system could work. But then, we have to be careful. And there's something else that's happening. So most ventilation strategies have like a MERV 8 or a MERV 13 filter in it. They don't always fit very tight with a lot of bypass. So the very
Yeah.
means by adding ventilation, whether it's a minimum code or whatever we're trying to accomplish, cause and effect, we could be causing other problems. And that would be loading the house with PM 2.5, loading the house with TVOCs from agriculture, from industry, from freeways and different things. And you're going to start hearing more and more about ground level ozone is starting to come up. We really got a handle on it when we started looking at emissions. We introduced catalytic converters to our vehicles, and those numbers started to climb, but they've come down to a manageable, like 50 ppm ambient outdoors. They're creeping up. So once we load a house, it's hard to unload it, especially if we're depending on ventilation to help us. You've heard the phrase "dilution is the solution for pollution." Well,
Yeah.
yeah, we can dilute carbon dioxide. We can even dilute, some TVOCs by means of ventilation. Offsetting building pressures with ventilation is determined really by how tight the house is. If we have a really loose house and we want to try to offset pressure differentials by way of ventilation, well, that's a tall order. You may find on a loose house, you're going to need 400, 500, 600 CFM to really flip those pressure differentials. On a tighter house, it's easier for obvious reasons. So being able to understand what the building is offering or what kind of challenges is the building offering us will determine greatly on our design criteria. And if we're able to actually offset pressures by way of ventilation, even if we could get close to neutral would be a good thing. And then, looking, I like to look at my worst case, any case depressurization by way of what the mechanical in the house has. So that would be kitchen exhaust, bathroom exhaust, exhaust inside like a utility, a laundry room, and even the dryer turned on is going to be taking air from the house to atmosphere. So I like to look at that worst case number, but I don't design the worst case. We got to take that. We need to know that number, and let's back that off a little bit. And let's look now. One of the biggest wild cards in what we try to do is behavioral. What are the occupants doing? What are their habits? And sometimes that wild card is hard to identify and overcome. But if we could back those off a little bit and let's look at some realistic numbers. Hey, I'm not going to have all these appliances running at full blast all the time. So maybe I can start backing some things off, and then we can use that as our design criteria for ventilation as well. Does that make sense?
Yeah, it does. But there's applications where you might have a high-rise building that has a makeup air running constantly because you have tenants on each floor that are using kitchen exhaust, bathroom exhaust, all these types of things. So on those types of systems, you'll essentially see like a makeup air unit on the roof, and it's bringing in 100% makeup air at all times. Most of the time, they'll have heat. Most of the time, well, I would say probably all of the time they'll have heat. Some of the time they'll have a DX coil to cool and dehumidify that air as well. So that's also an option, right? To have the device that's bringing in the air also has something to preheat or pre-cool or pre-dehumidify that air, so the mechanical in the actual space and the envelope is not taking such a brunt. But it's still energy usage at the end of the day. So give me your thoughts on that, John.
Most of what I deal with is single-family homes, not so much multifamily. Although I've done extensive work in multifamily in the past, but most of what I deal with now isn't. And so, so a dehumidifying ventilator that uses a refrigeration cycle to go ahead and wring that air out is going to be great. And then having a good mix. I mean, you could pre-mix that air with a little bit of supply to kind of mitigate temperature. But again, depending on how much, what volume of air, if you're only bringing in 64 CFM, that is not really going to be enough volume of air, depending on the volume of the house, to really start changing temperatures. Because it's going to mix. We're going to have good mix with our HVAC, and the thermostat should detect any kind of differences and run with that. But to your point, yeah, in commercial spaces and high rises, and I've been an air balance technician for many, many years, and I used to commission commercial kitchens. And a lot of times that makeup air would go through some kind of heating or some kind of tempering with the air before it brought such a large volume, depending on the size of the cook line.
This is going back to thermal comfort. What do you think of the term, hopefully I'm going to get this right, mean radiant temperature?
Our industry misses that big time, especially in higher end homes with higher end finishes. And so, for the viewers to understand, if you've got a lot of hard surfaces like granite countertops, marble floors, not a lot of soft, no carpeting, what happens is if we design our system and leave that out of the equation, we are changing the temperature of the air quickly, but we are not changing the temperature of all the mean surfaces. And so what happens is we're changing the temperature of the air in heating, and all those hard surfaces will absorb that heat. And then we're left with a big discrepancy. And now we've got the unit short cycling. But and a lot of things that our industry seems to miss too is when doing load calculations, they want to go from a manual J that gives us our BTU need and go right to a manual D. And it's like, you can't do a manual D until you do your manual S. You need your equipment selection to know what your fan performance is, extended fan performance. And then they also leave out manual T, all our termination points. The registers are real important because throw, spread, and mix are a big part of what we need to do to create a comfortable environment. And then
for sure,
just got the mean load in the house, and then everything goes sideways real quick. So that's a great point.
Yeah. So I was talking about that specific term with Nate Adams on his episode's probably going to be out before this one airs, so everybody will have heard that conversation. But we were just basically talking about the couch. When you come into a room, and the couch should be the same temperature as what the thermostat is set to. If the HVAC system is designed correctly, everything in that room should be close to the same temperature that you touch. Walls, couches, countertops, everything, right?
Yes, within reason. So, and I love Nate. I've known Nate for a long time. We've had some great conversations. And so a lot of people want to look at a building and look at stack effect. And stack effect is real. I mean, we've got wind, fan, and stack. And stack is real. And that's just the molecules in the air changing temperatures. And of course, the cold air will fall and the hot air will rise. And if you could look at it like you pouring cold water into a glass of warm water, the warm water will move its way up. I look closer at stratification. And the way I do that is I will take pieces of paper, and I will tape them 8 inches off the ground, halfway, 8 inches off the ceiling, and work all the way up. And then as I'm looking at stack, so it is stacking, I want to know stratification. And so that piece of paper, like the couch, will take on the temperature properties of the air, and I can actually temperature map my stratification. And I do this running heat and air conditioning because I want to see the effects of my air as it mixes. And this gives me the opportunity to really put numbers accurately to what's going on in the house. And so I'm looking at stack, but I'm also looking at, to your point, is the couch comfortable? Does that make sense?
Yeah. Yeah. I'm glad you brought up stratification because, I mean, most of my work has been a commercial service tech, and I could be walking across a warehouse floor and it's comfortable. But as soon as I get on a scissor lift and go to start working on a unit heater or something like that, the heat is all at the top of the building, right? The buildings that are designed correctly, they've got ceiling fans and they're blowing the air down, not so you can necessarily feel the breeze, because that's kind of uncomfortable as you're walking by a ceiling fan. It's kind of hitting on you. They're just moving at a slow pace, and it breaks up that stratification by pushing that warm air down to the floor, and then it just kind of circles back up, and it just continues to
Yeah.
rotate
They're
up
mixers.
and down. Yeah, exactly. So ceiling fans are great devices to break up stratification. Would you agree?
Yes, I do. We used to call them heaters because when you first turn them on, you feel that rush of warm air because you're actually popping that bubble. But yes, they're actually they're good mixers. I don't want us to lean heavily on a ceiling fan to make up for a poor design.
Oh, of course. Yeah. No. Yeah. I totally get you. Yeah.